Hello everyone, welcome back to this online class. Today we are going to look at the method of Taylor series expansion on how it is used to solve linear ordinary differential equations. Now we are given this question, we are asked to use Taylor series theorem to find a series solution of the following initial value problems. Part A, we have x squared plus 1 d squared y over dx squared minus 3 dy dx plus xy is equals to 0. And the initial conditions are y of 0 is equals to -1 and y prime of 0 is equals to 2. In part B, we have x times d squared y over dx squared plus x minus 1 dy dx plus xy is equals to 0. The initial conditions are y of 1 is equals to 2 and y prime of 1 is equals to 5. So this method of Taylor series is usually applicable when you have an ODE and the initial conditions, and that the initial conditions are specified at an ordinary point. So you can just write a note before even we look at part A. So in the note you can write that the method of Taylor series expansion is applicable when solving an initial value problem, IVP, and the initial conditions are specified at an ordinary point. You must ensure that that point x0 must be an ordinary point. This is what I mean. The value of x here, what you're calling x0, it must be an ordinary point. Even here, x0, this again is x0. Those points must be ordinary. So let's look at part A. In part A, I can write this in prime notation. So I can write part A. Our equation is x squared plus 1 y double prime. Remember, that's a function of x. Minus 3 y prime of x plus x times y. Remember, y is a function of x, is equals to 0. So look at the initial conditions. We have been given our initial conditions to be, let's start with the first one. So you can just say given that y of 0 is equals to -1, y prime of 0 is equals to 2. I need to know the solution. So you say let the solution be y of x. That's what you need to solve. Now expand this in Taylor series. To get, the Taylor series expansion of f of x or even y of x, any function of x, it will be y of x is equals to the sum from n is equals to 0 to infinity, then y and the nth derivative at x naught over n factorial x minus x naught raised to n. That is the Taylor series expansion of the function y of x. And so this is the same as writing, y at x naught plus y prime at x naught into x minus x naught plus y double prime at x naught over 2 factorial into x minus x naught squared plus y third prime at x naught over 3 factorial x minus x naught cubed plus so many other terms. But we need a third order Taylor series. Use Taylor series to find a series function. Of course, we can go up to third order, degree 3. So we can end there. So look at part A. What is our x naught in part A? Look at the initial conditions. X naught is equals to 0. That is in part A. So put x naught is equals to 0 to get. Put x naught is equals to 0 to get. Remember, this value of x naught, which is 0, is an ordinary point. This one here is an ordinary point of the ODE of the given ODE. If it is not ordinary, then you cannot use Taylor series expansion method. And you know how to find singular points and ordinary points. So when I put x naught is equals to 0, we are going to get y of x is equals to y naught, y of 0 I mean, plus y prime of 0 times x plus y double prime of 0 over 2 factorial x squared plus y third prime of 0 over 3 factorial x cubed plus so many other terms. So our solution should be in this form. This is how our solutions look like. Now the y of 0, y prime of 0, y double prime of 0, y third prime of 0, those are constants to be determined. Already we know y of 0 and y prime of 0. You see we are given here y of 0, already we know it. We also know y prime of 0 to be 2. So this is known. Again, this is also known. So what we don't know is y double prime and y third prime. So how do we find them? This is what you're going to do. So to find y double prime of 0, comma, put x is equals to 0 in the ODE and make y double prime of 0 the subject. Look at our ODE in prime notation. It is this one. So everywhere you see x, I'm going to use 0. So what will we have? We'll have 0 squared plus 1. Let me write it here. We are going to get 0 squared plus 1 times y double prime of 0 and then minus 3 times y prime of 0 plus 0 times y of 0. This multiplication is equals to 0. Of course, this is not there because you're multiplying by 0. So this simply means that, you see here, this is 1. So we'll have y double prime of 0 minus 3. What was y prime of 0? We got y prime of 0 was 2. Let me take you up there. We are going to substitute this value and also this value. Y prime of 0 is 2. So this is times 2. The other one was plus 0 times negative 1, which is still 0, is equals to 0. So from here, therefore, y double prime of 0 is equals to 6. That's what we find. Now we have found y double prime of 0. How do you find y third prime of 0? So you need to differentiate the ODE, because you see the ODE, the highest derivative is the second derivative. But here we need to find the third derivative. So I have to differentiate that ODE so that we can get some third derivative in that equation and then find that value when x is equals to 0. So you can write this, that to find y third prime of 0, you first of all differentiate the ODE, and put x is equals to 0. And then finally you need to make y third prime of 0 the subject, and make y third prime of 0 the subject. So let's start by differentiating the ODE. So let me write the ODE here. ODE that you are given, it was x squared plus 1 times y double prime of x minus 3y prime of x plus x times y of x is equals to 0. So we need to differentiate with respect to x. So you write differentiate both sides with respect to x. You know how to differentiate implicitly. So let's start by differentiating the first term. Of course, this you can let this to be u, and this other one is v, so that I can use product rule. Differentiate x squared plus 1, that is 2x. 2x, keeping the other one constant, y double prime of x, plus now I keep u constant, x squared plus 1 constant, differentiate v, that is y third prime of x. Similarly, minus 3, differentiate y prime, that will give us y double prime of x. Then plus, again here this is u, and this is v. So differentiate u, you get 1 times y of x plus x times y prime of x. That should be able to give us 0. So now put x is equals to 0. Put x is equals to 0. What are we going to get? We're going to get 2 times 0. 2 times 0 times y double prime of 0 plus 0 squared plus 1 times y third prime of 0 minus 3 times y double prime of 0 plus 1 times y of 0 plus 0 times y prime of 0 is equals to 0. Substitute what we know. Of course, where you are multiplying by 0, the result should be 0. So this multiplication should be 0 because I can see 0 there. Again, here we are multiplying by 0, so that should vanish. So, or now we have 1 times y y double prime of 0, y third prime I mean, of 0, that's this term, minus 3. What was y double prime of 0? We got 6. That's this term. The other one is plus 1 times y of 0 was negative 1. The right hand side should be equal to 0. So make y third prime the subject. So this simply means that that y third prime of 0 should be equal to, this is negative 18 minus 1. That's negative 19. Take it to the right hand side, you get positive 19. And you can proceed in the same manner. If you wanted to go up to the fourth derivative, you just differentiate the third derivative and proceed in the same manner. So now that we have found those constants, remember there are so many constants which you cannot write all of them. You just go up to the third derivative. So let's substitute them here. Let's call this equation star and replace those constants in the equation star so that you see what you get. So you can just say, hence equation star becomes, hence equation star becomes, it will now be y of x is equals to y naught, which was negative 1, y of 0 is negative 1, plus y prime of 0, which was 2. So plus 2 times x. Then y double prime, we got 6. So plus 6 over 2 factorial x squared plus 19 over 3 factorial x cubed plus so many other terms. Now this is a polynomial. So that means Taylor series can be used to approximate the solution of an ODE in terms of a polynomial. And you know how to find 2 factorial, 3 factorial, etc. So you can leave your answer in this form, or you can be able to simplify that further. But even if you write this, it's still fine. There are so many other terms that we have left up to infinity. You can't write everything. As long as you know how the series starts, that's fine. And remember, Taylor series is simply an approximate solution. That is part A. Let's look at part B. Part B, let me write the ODE in prime notation. Our ODE is x, y double prime of x, plus x minus 1, y prime of x minus 1, y prime of x, plus x y of x, that should give us 0. And what are the initial conditions? That y of 1 is equals to 2, and y prime of 1 is equals to 5. So in this case, our x naught was 1. This is our x naught, even here. So we let x naught be equal to 1. Now, let the solution be y of x. Let the solution be y of x. So we need to expand in Taylor series. Expand this solution in Taylor series. What do we get when you expand it? You're going to get y of x is equals to the sum from n is equals to 0 to infinity yn of x naught. The n there means the nth derivative of y at x is equals to x naught, and over n factorial x minus x naught raised to n. I also want to go up to the third order. So here we can open that summation so that we have y at x naught plus y prime at x naught, x minus x naught, plus y double prime at x naught over 2 factorial x minus x naught squared, plus y third prime at x naught over 3 factorial x minus x naught cubed, plus so many other terms. And we have said x naught is equals to 1. So we substitute 1 where there's x naught. So you can write here put x naught is equals to 1. So that we are going to get y of x is equals to, now it is y of 1 plus y prime of 1 x minus 1 plus y double prime of 1 over 2 factorial x minus 1 squared plus y third prime of 1 over 3 factorial x minus 1 cubed plus so many other terms. So, what do we know? We already know the value of y of 1 that is given. Also, we know y prime of 1 that is also given. So we know this, we also know this. We need to find y double prime of 1 and y third prime of 1. Already I've told you how to find them. So look at our ODE. Let me rewrite it. Of course, you can just write this so that the steps are clear. So you can write find y double prime of 1. So we are going, instead of writing so many things, just write here put x is equals to 1 into the ODE. Because already we have the ODE here. So when I substitute x is equals to 1, what are you going to get? You're going to get 1 times y double prime of 1 plus 1 minus 1 times y prime of 1 plus the other one is x, which is 1 times y of 1. That should be able to give us 0. So you can replace what we know, and you know where you're multiplying by 0, the result should be 0. So let me replace. You can just say or this is the same as y double prime of 1 plus 0 times y prime of 1. What was it? Y prime of 1 was 5. So I'll write here 5 plus 1 times, remember here there was a 1. 1 times y of 1 was 2. That should give us 0. And you see, here we are multiplying by 0, so I don't expect a value here. So from here, you can now be able to say that y double prime of 1 should be equal to negative 2. We have found it. The next thing, we need to find the third prime. So find y third prime. Y third prime of 1. So remember, we have found this. So we remain with the third prime, y third prime of 1. So what do we do? There are two steps here. We first of all need to differentiate the ODE. So what you do is to differentiate the ODE with respect to x. I don't need to write the ODE again because already we have it here. So let's just differentiate with respect to x. I'm going to use, of course, in the first term, we need to use differentiation by using the product rule. Because here we have a function of product of two functions of x. Even here, let this be u, and this one is v. Even here, you use product rule in each of those terms. We start with the first term, u prime v. U prime, you remember u is x, and v is y double prime. So u prime will give us 1, v is y double prime of x, plus now u v prime. V prime is now y third prime of x. That's the first term. Differentiate the second term. Again, u prime is 1 times y prime of x plus u, which is x minus 1, times y double prime of x. The third term, again, differentiate. That will give us 1 times y of x plus now x times y prime of x. That should be able to give us 0 on the right-hand side. So the next thing, you substitute the value of x. So you put x is equals to 1. Remember, normally x is equals to x naught. And in this case, our x naught is 1. So you put x is equals to 1. What are we going to get? It will now be 1 times y double prime of 1 plus 1 times y third prime of 1 plus 1 times y prime of 1 plus 1 minus 1 y double prime of 1 plus 1 times y of 1, that is y of 1 plus 1 times y prime of 1. That should be able to give us 0. Oh, now let's replace what we know. I don't expect a value where we are multiplying by 0. So here should vanish. Because see, 1 minus 1 is 0 times y double prime. Every time you're multiplying by 0, the result is 0. So you can just say here, or even those multiplication by 1, you don't need to write 1 times. You know it is the same value. So what is y prime of 1? y prime of 1, we got it to be 5. So just here, it is 5. Plus, what about y third prime? We don't know. No. Here it is y double prime. Y double prime, we got -2. It is this. Don't confuse. So let me rub what I've written. Here it is -2. It is y double prime, not y prime. So don't make those slight mistakes. So this one is -2. Y third prime, we don't know. Y double prime, we got 5. Remember, I'm through with this, and this. Now we go to this y of 1, that was 2. So 5 plus 2. And lastly, this one, y prime, that is another 5, is equals to 0. So you see the -2 and 2 will cancel. So 5 plus 5 is 10. So this means the third derivative at 1, y third prime at 1. What will it give us? -10. So let me bracket this again. That's what we have. So now we have found all those derivatives. And so we need to replace them back into our given ODE. We need to replace it back into the solution. Our solution was this. I can bracket it. This is our solution. You can call it equation star so that replace everything, those constants, into equation star. So you can say that hence equation star becomes, hence equation star becomes y of x is equals to, the first one is y of 1, which is 2, plus y prime of 1, which we have found to be 5, into x minus 1, plus y double prime of 1, that is -2. So plus -2, that should be negative, plus -2 over 2 factorial, x minus 1 squared, plus -10 over 3 factorial, x minus 1 cubed, plus so many other terms. And so if you simplify this one, this is what you're going to get. Or y of x is equals to 2 plus 5, and that is 5, plus 5 into x minus 1, remember 2 factorial is 2, so -2 over 2 factorial, that is simply -1, so it's -1 times x minus 1 squared, x minus 1, and that should be squared. Then 3 factorial is 6. So what is -10 over 6? That's -5 over 3. So we write here -5 over 3 x minus 1 cubed. And there are so many other terms which we have left out. So this one is our solution. Again, this is a series in powers of x minus 1. It is a polynomial. So that's how to use Taylor series or Taylor's theorem to solve initial value problems and where the initial conditions are specified at an ordinary point. Take note that even the one here, the x is equals to 1, is also an ordinary point of the ODE. That's I didn't mention that, but you can just say that this one is an ordinary point of the ODE. That is the ODE in part B. So, and I told you, if that point is not ordinary point, then you cannot use Taylor's theorem to solve that kind of ODE and the initial condition. That value must be ordinary for you to use this concept. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems involving Taylor's theorem as used in solving initial value problems. Bye-bye.